In this video we'll prepare potassium phthalimide, the reagent we plan to use in a future video. You might be put off making this from the literature because of the huge quantities of ethanol involved, but we'll show that there's a more efficient way. To start, we weighed out 17.5 grams of phthalimide. Check out our other video for details of how to make this yourself from phthalic anhydride. We're going to react the phthalimide with potassium hydroxide, so we've weighed out the 1.2 times molar excess of solid potassium hydroxide, which is 8 grams. After our ethyl chloroacetate preparation, we have a very funky looking stirred bar, and it seems as though the discoloration is permanent. We'll test it in this reaction and see if it really is permanently dyed black. We've got the 200 ml beaker set up with the stirred bar in on a heating mantle. And here's 100 ml of ethanol. We've also tried using slightly less ethanol and the reaction seemed to work just as well. Now we add the potassium hydroxide to the ethanol, and we crank up the stirring to get it to dissolve. This takes a couple of minutes, and the solution will heat up a little bit in the process. We've covered the top of the beaker with film just to stop any splashes because alcoholic potassium hydroxide is quite corrosive and we don't want this all over the place. While we're dissolving, we've switched on some heat and we're going to get the mixture up to nearly boiling point. The potassium hydroxide has now all dissolved, and you can now see from the slight bubbling at the bottom that we're close to boiling point of the ethanol. The temperature is around 75 degrees C. So now we're just going to start adding the phthalimide to the stirred potassium hydroxide solution, a little at a time to begin with, just in case the mixture decides to boil. There's a few bubbles coming off but nothing too vigorous. We keep on adding the phthalimide until it's all in. Phthalimide is only slightly soluble in hot ethanol and so it forms a suspension in the liquid. We're now all in and you can see a very faint yellow color developing in the mixture. We've covered the beaker with wrap again, and we're just going to stir and keep at around 70 degrees C for the next hour. The suspension first becomes thick, and then more fluid as time goes on. At the end of an hour it looks like this. The texture of the solid in suspension has changed and is now a very fine powder rather than the fluffy phthalimide crystal. We allowed the mixture to cool down to room temperature, and then set up for vacuum filtration. We wash the beaker and the precipitate with a small amount of absolute ethanol. Then let the powder dry on the pump. This took a bit of stirring and mixing around as the solid seemed to form a gel with the ethanol, but eventually we got it pretty dry. Here's the product: 23 grams of potassium phthalimide, which is very slightly damped with ethanol but is basically a quantitative yield from the starting phthalimide. It's a fine powder and with an interesting very faint yellow, almost green tint to it. Let's check there's no remaining phthalimide in the product. Here's a small beaker of water and some potassium phthalimide product. It dissolves, forming a perfectly clear solution. Phthalimide, on the other hand, is pretty much insoluble in cold water. Let's add a few drops of dilute sulfuric acid to this solution. The hydrogen ions from the sulfuric acid reattach to the nitrogen in the molecule, reforming phthalimide again as an insoluble precipitate. You normally would think of a nitrogen in an organic molecule acting as a base. But in the case of phthalimide it acts as an acid, being able to donate a hydrogen ion rather than receiving one. We'll leave it to you to work out why, but look at what lies on either side in the phthalimide molecule. Potassium phthalimide can be used in the synthesis of primary amines. Look out for this in a future video.